All right, so today we're gonna do the main result, which is the probability bound for the condition that we need to factor a number n for the factoring strategy. And this is just like putting the Chinese remainder theorem on the base results that we've already established. I want to go back to this claim that we had at the end of the last lecture. I want to go over it again to make sure that we understand what's going on here. So in here, what I want to prove is that the phi function of n, that the phi function, the Euler phi function has a multiplicative structure. So if you write the number inside of the phi function as its prime factorization, then you can write it, you can take the product out and keep the primes inside. And here, I don't think we need this for now. This is the argument of how we use the Chinese remainder theorem. N is going to be this number, which is a product of primes. So in particular, this is the prime factorization of some number n. And my argument here is that by the Chinese remainder theorem, the GCD of x with n is equal to 1 is equivalent to the GCD of, in here, maybe it's better to just say xi with xi with x equals to xi mod pi alpha I. So this are going to be equivalent statements, and I'm going to dive a little bit deeper into this equivalence, but essentially what then happens is that the phi function is equal to the number of elements of this set. The elements of C mod n that have GCD equal to 1. So the elements that satisfy this condition. And by the Chinese remainder theorem, we have that if you have an element here in this set, if you map it to this set using the map from the Chinese remainder theorem, then you're going to satisfy this condition for each of its components. So each of its components is going to be in each of these sets. And vice versa, if you have an element here, then by the where each of its components has GCD equal to 1, then by the Chinese remainder theorem, then you're going to be able to map back to this group. So we're going to have, or this set, we're going to have that this set and this set is going to be, they're going to be equal. So that means that the size of this set and this set is going to be the same. And here, when you have two sets, if you're looking at this cardinality of the product of two sets, A1, A2, this is equal to a cardinality of A1, A2. Right? And so in here, that means that when I take the cardinality of this right-hand side, it's going to be equal to the cardinality of each of the elements of the Cartesian product of sets. So in here, I have that the cardinality of this is equal to this, so I just take and so on until here, and so I take the product of all of those, and I get the equality. So this is the main idea, and I want to take some time to go through this, because once we establish this, that if we have an element in this set, then by the Chinese remainder theorem, it's going to imply that this are going to be the same, and then we have equality. So the top is the statement that I want, is that the GCD mod n is equal to 1 is equivalent to the GCD mod pi to the alpha I is equal to 1 for every I. And in here, the interpretation that I have for the GCD of x mod, the GCD of x and n equals 1, I recall that this is equivalent, this condition is equivalent to the existence of some element y such that x times y is equal to 1 mod n, to the inverse of x mod n. And this is where the fact that the Chinese remainder theorem satisfies or respects the multiplicative structure comes in. Because if we can find an inverse on one side of the bijection, then we're going to be able to find an inverse on the other side of the bijection. So that means that the GCDs are going to be equal to 1. So, and this is what happens. So in here, by the Chinese remainder theorem, if we have a pair of elements, x and y, then by the Chinese remainder theorem, there's a bijection of elements xi, yi that map to each other. So x and the what, not a tuple, it's a m tuple of this xi's are going to map to this, and this y is going to map to this yi's by the Chinese remainder theorem, and it's going to be in bijection. And then if we look at the multiplicative structure here, we're going to have that by the fact that the GCD is equal to 1, that there's going to be this product xy is equal to 1 mod n. And then if we look now at this identity, and since the Chinese remainder theorem satisfies the multiplicative structure, it's going to mean that this xi times yi is going to be equal to 1 mod pi alpha I. So by the fact that we have an inverse here, it's going to imply that we have inverses on the right-hand side. So it's going to imply this statement right here. And similarly, you can just, since this is everything's by bijections, so you can take the argument in the opposite direction. So we have that the GCDs equal to 1 here is equal to the fact that the GCDs equal to 1 are equal to 1 here. So we can then, this establishes this equality of elements, of sets. Does that make sense? And then we just go straight through. We just look at the size of each set on the left and the right-hand side, and they have to be equal. Questions? All right. So we're moving to the main claim of this factoring algorithm. That if we take n, which has this prime factorization, then the probability that the order of x modulo n is even, and that x to the order divided by 2 is not equal to minus 1 modulo n is greater than or equal to 1 minus 2 to the m minus 1. I think this is a minus 1. I think the textbook says m, and I think that's a typo. So we'll go through the proof. And this is if x is chosen uniformly from this set of elements that have GCD equal to 1, that have inverses. So this is what we're trying to prove. And I guess we should recall if m is equal to 1, then we have the statement that probability that 2 to the d divides the order of x is equal to 1/2 with p minus 1 is equal to 2d times, we'll say k, where k is odd. And in particular, 2d is the highest power of, or d is the highest power of 2 in p minus 1. So this is the statement that we had already proven, and this is in the case that n is equal to p to the alpha. So the prime factorization just includes one prime. And here we're trying to generalize it to a case where the product of, where n is equal to a product of more than one prime. So the statement is, so in here, let's see. So in here, we definitely have that for m equals 1, we definitely have that with probability greater than or equal to 1/2, it's going to be, actually, yeah. With probability greater than or equal to 1/2, it's going to be even, the order, and we wanted that the x to the order divided by 2 is not equal to minus 1. I forgot to check that explicitly, but I think we'll see. We'll see how it works in general, because we're going to rely on this statement to prove this statement. And if we put m is equal to 1, then this bound is just going to be equal to 1 minus 1, which is equal to 0. So I guess in that case, it's going to be trivially true. And in the case where m is equal to 1, we have a different strategy to do the factorization of m. So in the factoring strategy that we have, we assume that there's two distinct primes. So we have that. Questions? All right. So again, the technique is to use the Chinese remainder theorem and use the result that we have for m equals 1. And what we've shown already is that we have this equality, this bijection between the elements that have GCD equal to 1 on this left-hand side and the elements that have GCD equal to 1 component-wise. So when we're choosing x uniformly from this set, it's going to be equal to, it's equivalent to choosing each xi uniformly from each of these sets, z mod pi to the alpha I. So what we're going to do is that we're going to move our randomness from this axis to this axis. And the randomness in these cases, we can control them because we have this statement for each of these cases. So now we can move to the randomness of each component and just uniform in each component. And then uniform and independent from the other components. So we can just work, we can work on each of the components separately, and to get the probability of the left-hand side, we just take the product. So essentially, what this is saying is that if we have the probability function of the left-hand side, this is going to be a product of probability functions on the right-hand side. And we can control the probability functions on the right-hand side. So that's how we're going to get through it. So the statement that we're trying to prove is this probability that the order is even, and if you take x to the order divided by 2, it's not equal to -1, and it's greater than this number. And by taking the complement of this event, which is that the order is not even, or x to the order divided by 2 is equal to -1 mod n is less than equal to 1 over 2 to the m. And again, I think this is 2 to the m minus 1. So instead of proving this inequality, we're going to take the complement of this and prove this inequality. And in particular, we have that the probability that we're interested is the union of two events, either this or this. So I have that E1 is equal to this event, and E2 is equal to this event. So more precisely here, the event E1 is that the order is not even, and the event E2 is that the x to the order divided by 2 is equal to -1 mod n. So I can split up, I can write this up, this event as the union of two events. And to write this probability, I can actually write it as the sum of two probabilities. The probability of E1, so this region here, plus the probability of E1 complement intersection E2. So that's going to be this region. So I'm splitting it up into two probability events. And with the base statement that we have, this is going to be easy to bound. And again, with the same base statement, we're also going to be able to compute this probability. And that way we can compute the bound for this union of two events. Questions? So I'm going to start with controlling the probability of this event, and then I'm going to control the probability of this event. So the first event that I want to control is that the order of x mod n is not even. So I set r to be the order of x mod n, which means that x to the r is equal to 1 mod n, and r is minimal. And by the Chinese remainder theorem, I have that xi to the r is equal to 1 mod pi alpha I for every I. And this means that the order of xi, pi to the alpha I, which I denote ri, divides r. Because we did this exercise a few classes ago, that the order of ri of an element is going to always divide any power that is equal to 1. The exponent of any power that is equal to 1. So since we have that xi to the r is equal to 1, then ri, the order of xi, must divide r. Good? Now, in here, we're assuming, in this event, we're assuming that the order n is on, that r is on in this event. So this is the definition of this event. And we have that since r is on, so in here we have r is on, then this means that this ri has to be on. Because if this is even, then it's not going to divide, an even number doesn't divide an odd number. So this implies that each of these ri's is on. So we have that since r is on, then Ri must be odd for every I. And then this is where we use the statement for the base case. So for the base case, we had that the probability that 2di divides Ri is equal to 1/2. So if I take the complement of that event, and in particular, we also have that di is greater than or equal to 1. So with probability greater, since di is greater than or equal to 1, we know that with probability greater than or equal to 1/2, Ri is going to be even. So if this, in particular, if this is true, we know that Ri is even. So for Ri to be odd, then this necessarily has to be false. So we can bound the probability of Ri being odd by taking the complement of this, by negating this. So we take the complement of this event, and we obtain this inequality that the probability of Ri being odd is going to be equal to 1/2. And the reason that we don't have equality is that in this event that 2d divides Ri, since di could be strictly greater than 1, then potentially the complement of 2di divides Ri could include 2di minus 1 divides Ri. So in the complement that of 2di divides Ri, we could encounter the case where 2di minus 1 divides Ri, which still makes it even. So the right-hand side contains Ri being odd, but contains also other possibilities where Ri could be even. So that's why it's an upper bound. And in here, we just need to have an upper bound of 1/2 for Ri being odd. So this is going to be Ri being, the probability of Ri being odd is equal to that. And then if we put all the prime components together, we want to show, and this is true for every I, so the probability that all the Ri's are odd, since these are independent, is the probability that R1 is odd times the probability that R2 is odd, and so on until the probability of Rm is odd. And for each of them, we have an upper bound of 1/2. And we just multiply them all together, and we get an upper bound of 1/2 to the m. So that's controlling the first event, that we want the order to be odd. So it's bounded above by 1/2 to the m. Questions? Now we want to control E2 intersect E1 complement. And in this case, we have that x to the r/2 is equal to -1 mod n, and r is even. So in this event, in this intersection of events, we have that xr/2 is equal to -1 mod n. And by the Chinese remainder theorem, each component, after we map it to the m tuple of elements, must be equal to -1 mod pi alpha I for every I. And since we have that xi to the r/2 is equal to -1, then we have that the order of xi mod pi alpha I, ri, denoted ri, does not divide r over 2. And we can see that that's true, because otherwise if we write, if ri divided r over 2, then we could write r over 2 as a multiple of ri, so ri times some integer l. Then we would have xi to the r over 2 is equal to xi to the ril, and then we move in the ri first, we compute xi to the ri first, and since ri is the order of xi, then this would be equal to 1, and then 1 to the l is 1, and we have that xi to the r over 2 is equal to 1 mod pi alpha I. So this would give us a contradiction, because we know that xi to the r over 2 is equal to minus 1 mod pi alpha I. So we have this conclusion that ri doesn't divide r over 2. Good? Now, on the other hand, we have that rj divides r, since by the Chinese remainder theorem, we have that xi to the r is equal to 1 mod pi alpha I. And this is what we did when we were bounding. We used this fact when we were bounding the probability of E1. So we have that rj divides r, but rj does not divide r over 2. So if we set rj is equal to 2 to the dj kj, and r is equal to 2 to the dk, where k and kj are odd, then we're going to have these two statements. We can write them as follows. 2 to the dj kj is going to divide 2 to the d times k. So this statement, I just rewrote it here. And then we're going to have that rj 2 to the dj kj does not divide r over 2 to the d minus 1 k. And the conclusion here, if you look at these two statements, where you have that this divides this for every j, and this is true for every j, and for every j, you're going to have that this number is going to divide this number, but if you remove a power of 2 from the right-hand side, then it's not going to divide it anymore. So the only conclusion you can draw here is that dj has to equal to d. And that's why it cannot divide it anymore once you remove a power of 2. So we obtain the conclusion that for all the powers of xi mod pi to the alpha I, they have the same power 2 to the d, 2 to the d times kj. So they all contain this factor, the same power of 2 factor. So here, what this means is that for the probability of E2 intersect E1 complement, that's equal to a probability that di is equal to d for every I, which is equal to the probability that 2 to the di divides ri for every I. And we can break it up into each of the components by using the product, using independence. And we have that each of the statements is probability of 2 di divides ri, and this is our base case that we've started with. And the probability of each of these events is equal to 1/2. So it's just 1/2 times 1/2 times 1/2. And we have that this probability is equal to 1/2 to the m. And in here, now I use this this identity, that the probability of E1 union E2 is going to be equal to this probability. I bounded this probability by this, and I say that this probability is equal to this. And this is where I get the -1. That's not in the textbook because I'm adding these two probabilities. And that's the result. And that's how we obtain it. And really it is by using the Chinese remainder theorem to glue together all the base cases. Questions? All right. That's it for the lecture.